Every time you see .t in Python, q.t, k.t, w.t, that is the transpose. It is the single most common operation after matrix multiply in all of AI code. We saw it in video 8 when we needed shapes to align. Today we understand it completely, what it does to every element, why symmetric matrices arise naturally from it, and where both appear throughout deep learning and monitoring systems. The transpose of A is written as superscript T. The rule is, element A at row I, column J moves to position row J, column I in the result. Every index pair swaps. So A, 0, 1, which was in row 0, column 1, becomes a transpose 1, 0, row 1, column 0. The shape flips. A 3, 2 matrix becomes 2, 3 after transpose. 4 properties to memorize. Transposing twice gives you back the original. The shape flips M by N to N by M. The transpose of a product reverses the order. A B transpose equals B transpose A transpose, not A transpose B transpose. This order reversal is critical in backpropagation. And transpose distributes over addition without reversing order. A symmetric matrix is a square matrix that equals its own transpose. A equals a transpose. Equivalently, A at row I column J always equals A at row J column I. Visually, the matrix is a mirror image of itself across the main diagonal. The diagonal elements can be anything, they are their own transpose. The off-diagonal elements always come in matched pairs. If you see the value 7 at position row 0, column 1, you must also see 7 at row 1, column 0. Check symmetry in NumPy with NP. All close of A and AT, use all close not the double equals sign, because floating point comparison needs tolerance. 4 symmetric matrices you will encounter constantly in AI. First, the covariance matrix. Computed as X transpose at X divided by N, where X is your centered data. Entry at row I, column J is the covariance of feature I with feature J, which equals feature J with feature I, so it is always symmetric. Second, the gram matrix, X transpose at X, used in style transfer and kernel methods. Third, attention scores. The raw, SQ by SQ, score matrix in transformers is produced by Q at K transpose, building a full matrix of how much every token attends to every other. Fourth, correlation matrices for monitoring metrics. Correlation of CPU with memory equals correlation of memory with CPU, always symmetric. 3 NumPy patterns. Transpose. AT is the attribute, use this, it is cleanest. A transpose also works. Check the shape changes from 2, 3, 2, 3, 2. For symmetry checking, NP. All close of A and AT always use all close for floating point matrices, never the double equals sign. For building a covariance matrix, center your data by subtracting the mean, then compute X-centered transpose at X-centered divided by N. Always verify with NP. All close, any correct covariance computation should pass this check. 2 definitions to know cold. Transpose, A, I, J, becomes a transpose, J, I, indices swap, shape flips from M, N, to N, M. Symmetric, A equals a transpose, meaning A, I, J, equals A, J, I, for all I and J. Exercise, create a 3, 4, matrix A compute. A transpose, verify shape is 4, 3. Then compute a transpose at A, the result is always symmetric. Verify with NP, all close. This is the gram matrix. For the intuition drill, write out the shapes for Q at K transpose in attention. Why is the transpose necessary? Answer that and you understand the operation deeply. You now have a complete picture of the transpose, where every element goes, why symmetric matrices arise from it, and how to verify symmetry in code. Video 10 covers matrix inverse and solving linear systems. Subscribe so it is ready. Drop your Q at K transpose shape explanation in the comments. Writing it out is the best way to cement it. See you in video 10.